The universe is filled with a variety of celestial objects, ranging from planets and stars to dust and gas. But there are also dark regions that we cannot see, such as black holes. The James Webb Space Telescope is helping scientists peer into the dark side of the universe. Webb has given scientists an unprecedented view with its powerful infrared vision and extremely high spatial resolution. Webb can pierce through the shroud of dust surrounding the nucleus to reveal hot gas near the active black holes and measure the velocity of bright outflows. Webb will address several key questions in order to help us understand the story of the star and planet formation. To unravel the birth and early evolution of stars and planets, we need to be able to peer into the hearts of dense and dusty cloud cores, where star formation begins. These regions cannot be observed at visible light wavelengths, as the dust would make such regions opaque and must be observed at infrared wavelengths. Many of the star's properties, how long they live, what colour they appear, how they die, are largely determined by how massive they are. But what happens to stars in the final moments of their lives? Why some of them collapse to become black holes? What will happen to the Sun? Will it become a black hole or perhaps a neutron star? We can only observe our Sun at this particular time of its life, but scientists can see its past and future by looking at similar stars earlier or later in their cycle. The Sun will need to be about 20 times more massive to end its life as a black hole. Some smaller stars are big enough to go supernova, but too small to become black holes. They'll collapse into superdense structures called neutron stars after exploding as a supernova, but the Sun's not big enough for this fate either. In some 6 billion years it will end up as a white dwarf, a small, dense remnant of a star that glows from leftover heat. The process will start about 5 billion years from now, when the Sun begins to run out of fuel. Large stars are a bit different. About 75% of the mass of the star is ejected into space in the supernova. The fate of the leftover core depends on its mass. If the leftover core is about 1.4 to 5 times the mass of our Sun, it will collapse into a neutron star. If the core is larger, it will collapse into a black hole.
So what happens is a star is holding itself up against the pull of its own gravity, which is trying to squash it down because of the nuclear reactions in the core of the star. So because the star shines, and that produces a pressure, if you like, that holds the thing up. But it can't keep burning its fuel forever. And when it runs out, gravity will take over again. And in the case of the most massive stars, then no known physical process can stop the collapse. So gravity wins. So it just collapses and collapses and collapses, as far as we know, forever. So you get an infinitely dense point of what, I can't even call it matter. It's gone, really. All there is left is the gravity, in some sense. We don't know the physics when these things get so dense and so tiny. We don't know what the physics is. So it may well not be just this infinitely dense point. We just don't know. But so we give it a name, the singularity. But all that's left that you can observe in the universe is the gravity. All the matter is kind of gone. So it's one of the great questions in physics. And it's very strange that strange things happen. For example, we can work out what the circumference of a black hole is. So we can go around the event horizon and say, well, it's so big. But if you say, what's the distance from the event horizon to the center? It can be infinitely big. The radius can be a lot bigger than the circumference would suggest because of the curvature and bending of space and time.
Black holes are some of the most fascinating and mind-bending objects in the cosmos. Though detecting black holes is a complex job, estimates from NASA suggest there could be as many as 10 million to a billion stellar black holes in the Milky Way alone. They cannot be seen because strong gravity pulls all of the light into the middle of the black hole. Scientists observe black holes indirectly by the way their gravity affects stars and pulls matter into orbit. As gas flows around a black hole, it heats up, paradoxically making these invisible objects into some of the brightest things in the entire universe. As a result, we can see some of the black holes from billions of light years away. In principle, any object, even a rock, can be made into a black hole by squeezing it into tiny enough volume. Under these conditions, the object continues to collapse under its own weight, crushing itself down to zero size. However, according to Einstein's theory, the object's mass and gravity remain behind, in the form of an extreme distortion of the space and time around it. This distortion of space and time is the black hole.
Einstein didn't know that there were such things as black holes when he published the theory. He certainly didn't know that we'd ever see them collide together. He certainly didn't know that there were ripples in the fabric of the cosmos, although he predicted that slightly later, that would carry the information, just like light carries the information from distant stars, so the ripples in the universe can carry information from collisions of black holes. So we've entered a new age of astronomy where we can watch black holes collide. To reverse Stephen Hawking's area theorem, which seems to have been proved by these collisions now, says that if you collide two black holes together, then the area of the horizon around the new black hole has got to be bigger than the area of the horizons of the two little black holes. And that seems to be what we've seen. What is that thing, the event horizon? It's the area around the black hole from which light can't escape. If you go into a black hole, which you could do, if it's sufficiently big or sufficiently massive, you could fall in through this point, this sort of region of space around the hole. And you could easily fall in. And what happened when you fall in is that you could never get out again. And you couldn't even send a signal of light out of the black hole because the gravity is so strong that the light can't escape. And the region from which the light can't escape is called the event horizon, or inside this event horizon. And that's what you see with the black hole. If you could float around and see one, you wouldn't see anything because it would be black, but you would see this sphere or this shape in space from which no light would emerge, and around which all the light from the distant stars and the galaxies would bend and curve and be warped.
Black holes can be big or small. Scientists think the smallest black holes are as small as just one atom. These black holes are very tiny but have the mass of a large mountain. The largest black holes are called supermassive. These black holes have masses that are more than 1 million suns together. Scientists have found proof that every large galaxy contains a supermassive black hole at its centre. The supermassive black hole at the centre of the Milky Way is called Sagittarius A. It has a mass equal to about 4 million suns. However, black holes are even stranger than that. As you get closer to a black hole, the flow of time slows down, compared to the flow of time far from the hole. According to Einstein's theory, any massive body produces this effect. Earth's gravity is so weak that the slowing of time is not noticeable, but the effect has been confirmed using sensitive instruments. For example, at sea level, you age 1/1000th of a less second every year than you would if you lived at the top of Mount Everest. Near a black hole, the slowing of time is extreme. From the viewpoint of an observer outside the black hole, time stops. For example, an object falling through the hole would appear frozen in time at the edge of the hole.
Now, the black hole then is made from warped space. Things can't get out of it. But one way to understand that things can't get out of it is because of warped time. Time slows as you near the horizon of a black hole. And so if you're hovering here and not falling through, the closer you get to the horizon, the slower time is flowing compared to what you see very far away. In the movie Interstellar, for those of you who saw it, Cooper goes down near the horizon of a black hole. He's there for a few hours, comes back, and his daughter has aged from age 11 to becoming a great theoretical physicist of age 28. So anyway, so you see this in the movie. If you fall through the horizon, then time doesn't simply slow down. Time flows in a direction you would have thought was a space direction toward the singularity. And so that's one reason you can't get out. It's because you cannot move backward against the local flow of time.
It is said that fact is sometimes stranger than fiction, and nowhere is more true in the case of black holes. Thanks for watching. Did you like this video? Then show your support by subscribing and ringing the bell to never miss videos like this.